discussing this thing about the Mosfets. In that, we have said different region operation of Mosfet. The MOS capacitor, and then how or when they will be on, when they will be operating in saturation region, cutoff region, or linear region, that we have discussed. Now we'll continue from there. Today we'll try to catch up what we have left behind. Okay. So from the last lecture and the currently given the equations, what you understand is if I say that IDS equals to 0 for P Mosfet, IDS equals to 0, that is cutoff region when VGS greater than VT. So if I give these values for the P Mosfet here at the top encircled here, can somebody say that in which region it is operating? Aman?
Yes, sir.
Okay. Are you?
Sir, it was working on. Yes, sir. It was working on saturation region.
And now I am asking the question for NMOS, not NMOSFET, P Mosfet. Now you have to think of. Let me try it again. This is, I'm drawing. This is P Mosfet. 1 volt is here, and 0.5 volt is here, for example, and VTP equals to minus 0.4, and this is 1 volt. Body is also 1 volt. Okay, gate is 0.2 volt, say. So in which region it is operating? That is the question. Equations are given, conditions are given for linear as well as saturation region. In the green color it was for P Mosfet, and something I have written with red color, that is for P Mosfet. Just reverse the direction. Earlier it was VGS less than VT, then cut off for N Mosfet. Now it is cut off. P Mosfet is cut off in cut off region when VGS greater than VT. Yes, still. Similarly for linear region, I have written this thing. VGS should be less than VT, and VDS should be greater than VGS plus VT. Then linear region. In saturation region for P Mosfet, VGS less than VT, VDS less than or equals to VGS plus VT. With this knowledge, can you tell which region, in which region this Mosfet is occurring, I mean working or operating? Forgot yesterday in the last class we were discussing. Yes, Pratham.
Sir, not remembering.
Okay. Thing is that I don't have blank page. Okay. Let me try to write here. I need a blank page. Let me see. No blank page is here. Okay. Here only I'll try to say something. Now we are talking about P Mosfets, right? Let me take different color. Yes. We're talking about Mosfet. One is cutoff region. Cutoff means it is not conducting. Cutoff region. Current will be what? ID will be 0. Condition is what? VGS greater than VT now. It is VTP, let me write. VGS greater than VTP. In case of MOSFET, VGS less than VT, and then it is cutoff region. And for linear region, ID equals to mu P here, mu P C ox W by L, okay, into VGS minus VTP into VDS minus VDS square by 2. This is the equation. Condition is what? Linear region condition is VDS. Earlier it was less than. For MOSFET it was less than VGS minus VT. Here it is greater than VGS minus VTP. Okay, of course that condition is valid. I mean, you have to put other condition always. That is VGS less than VTP. This condition, these two condition you remember for linear region. Similarly for saturation region ID equals to mu P C ox W by L divided by 2 into VGS minus VTP whole square. Okay. Now its condition is VGS should be less than VTP and VDS should be less than equals to VGS minus VTP. These are the conditions. Now I am using the symbol of P Mosfet to say I am putting 1 volt here. It is 0.2 volt here and 0.5 volt here. Now of course this is body, say VDD equals to 1 volt and VTP minus 0.4 volt. Tell region of operation. हाँ दार्सी बोलिए. अच्छा ठीक है, मैं आ जाऊंगा. याद इसको भेज दूं, शशांक को भेज देते हैं. ठीक है, ओके, थैंक यू. Once again I was disturbed. So my question is understood? Pratham, Aman,
Yes, sir.
Harsh Tripathi, are you here? At the last class you are not there, I think. So
Yes, sir.
question is whether you have understood the question or not. First question is that. If you have understood the question, then what is that question? MOSFETs operate in 3 regions. In the last class we have discussed about the MOSFETs. I wrote the conditions also, and one this kind of figure I have given along with the terminal voltages, and you could tell in which region it was operating. Now it is about P MOSFETs. Okay, conditions and equations of the currents I have written. Now you tell in which region this MOSFET is operating. After that, we'll go ahead with the current course curriculum.
Sir, cutoff.
Okay, cutoff you are telling. Okay. Anybody else? Anything other than his? Aman? Aman, tell. Aman, tell. Aman, Bushra,
Sir,
Ashtipati. Aman, tell.
yes,
What
sir.
is your
I have a
opinion?
little bit doubt that for threshold voltage, we take a direct the given value or its modulus.
See, you have to understand whatever equation is given. Based on that, you understand. Then I'll be explaining. You think of whatever you are thinking, and then tell. Then I'll start uh, describing thing. Okay.
Sir, saturation.
Saturation. Okay. One is cutoff. One is saturation. Aman, you want to say something?
Sir, in saturation.
Saturation. Okay. Let us see. Condition for saturation is what will take up. Is it going to be true or not? Condition for saturation is this one. Okay. First of all, you check this one. VGS should be less than VTP, then only MOSFET is on. This is off, and these two are on condition. Remember, linear saturation is on condition. First, MOSFET should be on, then only we can start saying whether it is working in saturation or linear. Okay. First, we'll check up whether it is on or off. Pratham has said it is off. Let us say, see that VGS. What is VGS? VGS should be less than VTP. That is the condition. VGS is what?
Minus 0.3 volt.
Pratham, VGS is what?
Minus 0.3.
Harshipati?
Sir, minus 0.8.
Yeah, you're right. See, in the last lecture I have said, again I am repeating, and this you must know in your life, that for a P MOSFET, I am not putting a bubble. This is a P MOSFET. Whereas I am putting a bubble here at the gate in case of N MOSFET. So for a P MOSFET, this is gate obviously. This is also gate obviously for N MOSFET as well as P MOSFET. But this is body. Okay. This is also body terminal or substrate terminal. There is no doubt in that. But out of this two terminal, left over two terminal, top and bottom, which one is what? It is a symmetrical device. Remember that structure is in front of you. It is totally symmetrical device. Okay. There is no preference that which one you will call drain, which one you will call source. But yes, you have to remember that that node, in case of N MOSFET, that node is drain, which is at higher potential. Yes. And the other one is source. You're getting my point. Other node is source. Source is this one in this case, and drain is this one is scaled if and only if this is at higher potential. Say it is 1 volt, this may be 0.5 volt or so. Should be less than 1 volt. Then only you can say. Otherwise, if say it is otherwise, say it is 1.5 volt at the bottom and at the top it is 1 volt, then definitely this definition doesn't shoot. We have to say this. Could you understand? Yes or no? Aman?
Yes, sir.
So drain or source will be decided by the potential value. Okay, which one is higher? That one is the one which is higher in terms of potential, that is drain, other one is source. If you think of the flow of carrier, then we have seen that in this say electrons are moving in this direction. So this one I can say source. This one is drain, right? Current in this opposite direction. So source means it is sourcing the carrier. That way you remember. In case of Mosfet, the negative terminal of the battery or lower voltage, you can say, wherever lower voltage is there, that will be the source, because in this case in Mosfet, carrier is electrons. So electron will flow in this direction. Okay, you can think of that. Let me regain the earlier values, otherwise you'll be confused. Earlier values. So if I put that is 1 volt, this is say 0 volt. This must be source, this must be drain, this must be source. In other words, what we have done, we have connected a battery. Okay, these electrons in the channel are getting repelled by this in this direction. Okay, and in the positive term, the battery is attracting those electrons. Okay, electrons are flowing in this way, and conventional current, of course, in this direction. So source of the carrier in Mosfet is electrons, and that is being sourced by source terminal. Can you remember this way? Yes or no?
Yes, sir.
So the terminal which is sourcing the carrier is source, and it will be sourcing carrier if it is at a lower potential. H is at lower potential, and D is at higher potential. That is in Mosfet. Case is over. For P Mosfet, it is opposite. For P Mosfet, remember that this is P Mosfet, say 1 volt. This is 0 volt. Let us think of 0 volt. So body is in this way. Body of P Mosfet is connected to highest potential, remember. And in Mosfet, body is connected to lowest potential, normally ground. And this is normally VDD denoted by this kind of symbol. Okay. If it is supply voltage is 1, VDD is equal to 1, then it is connected to 1 volt. If it is some other voltage, it will be connected to that voltage. Okay. Now this is gate, obviously no problem. But out of these two terminal, which one is what? Yes, can you tell which one is what? Again, I am telling you, think of the terminal which is sourcing the carrier, that is source. Other one is drain. Think of what is the yes?
1 voltage source.
Sourcing the carrier. What is the carrier in P Mosfet? Current carrier. In P Mosfet, what is the current carrier? In the last lecture, we have discussed. Think of, we have discussed.
Electrons.
Electrons is in case of Mosfet. We have started discussing yesterday with Mosfet. I don't have blank page, otherwise I could again start. Let me say here. Space is not there, but still I'll try to discuss here only. P Mosfet's substrate or well is N well. Okay, you'll make P plus here, another P plus here. Okay, I mean by ion implantation, you'll be applying silicon dioxide. Over that, you'll have the gate material. So again, it is nothing but a capacitor, as you can see here right side. So you'll be applying negative potential with respect to source. This is source. This we call drain. Just opposite thing. Okay. And if you apply a negative voltage at the gate with respect to source, then what will happen? Negative voltage means you are depositing negative charges here. It is a n well, so electrons are there, n type material. Okay, very few electrons are there. It is lightly doped. That's why. Okay, these electrons will be repelled here initially if your gate voltage is less negative with respect to source. So, leaving behind what kind of ion? Tell me. If electrons are repelled by the charges, negative charges deposited at the top terminal, that is gate terminal, what will be happening? Electrons are repelled, what ions will be left behind? Tell.
Sir, holes.
Not holes, they are positive
I mean,
ions, right? Positive ions will be left behind. See, basically it is n-type means what? Substrate is n-type means what? Pentavalent atom is there. In your substrate, your silicon is having 4 electrons at the outer shell. You have doped it with pentavalent. Okay, so pentavalent atom having 5 electrons at the outer shell, a phosphorus for example. If that electron is removed or pushed away, then what is left behind? A positive ion will be left behind. Okay, but if your negative charge is increased, VGS is more negative now, then more electrons will be deposited at the gate material, and hence the electrical field will be stronger. So attraction, repulsion, you can say, or attraction for the minority holes here and there due to thermally generated electron hole pair. So minority holes will be lined up here. Okay, the way it was electron in this case, now it is holes. Holes are lined up here. Inversion layer is here hole because you have applied negative potential at the gate with respect to source. So if you connect now a voltage, external voltage between these two, so that I can show you with this way. Negative terminal of the battery is connected to the drain and source is connected with a positive terminal of the battery. Say normally it is shown like this, PDD. Okay, so maybe 1 volt, and out of this, I mean, what will happen to this? Now tell me, in which direction current will flow? In this channel, you have excess holes, which we are calling inversion layer. Earlier it was inversion layer electrons. The electrons here, in case of N Mosfets, it was N plus type. Okay. Now it is P plus type. 2 region we have doped with boron possibly. Okay. On the N well or N substrate, N type substrate you can think of. Then what will happen to the carrier which are gathered here due to the electrical field at the gate? Those carriers are thermally generated holes. Okay, so tell me what will happen to this? How current will flow, in which direction current will flow? Pratham, Aman,
So
yes,
from source to drain.
Yes, holes will be flowing from source to drain because the positive terminal is connected to the source. So, and those positive terminal will be pushing the electrons away. Okay, whereas the negative terminal of the battery is going to attract it. So, holes flow is the conventional current flow direction, same direction. So, here also you see the carrier is hole and source terminal is sourcing the carriers for the currents. Could you understand? So, source for N MOSFET and P MOSFET is that terminal which sources the carrier. In case of N MOSFET, we know that carrier is electrons. So, from source terminal, electrons flow, current will be in the opposite direction. In case of P MOSFET, source is hole, current source is hole, and it flows from source to drain. So, normally, you can very well understand that hole is moving from source to drain means what? Hole is at higher potential and then the drain. Anyway, could you understand which one should be a higher potential drain, which one will be a source in case of P MOSFETs? Yes or no? Tell somebody.
Yes, sir.
So which one I'll call a drain and which one source in this case diagram? Tell me. The symbol I have used here.
Sir, 1 volt is source.
1 volt is source, and the bottom one is drain. This could be 0 or any potential, doesn't matter. Say I'm writing 0.5. Okay? 0.5. No problem. Still no problem because potential difference is there. So obviously there will be push and pull. Drain source will be pushing the holes here. Okay? Holes here pushing, and it will be coming to this side, generating the current. Now, question is what? Our question is in which region it is operating. Okay, in which region the MOSFET is operating. That was the question. Tell if the source is at 1 volt, then in which region is going to operate. BTP I have written as minus 0.4 volt. Now come up. Tell. Gate voltage I have given 0.2 volt. Tell. Not understanding still.
Sir, in saturation region.
Saturation region. Okay. Now let us check. Saturation region condition is given here for us. Okay. So it is VDS should be less than or equals to V. What is the VDS? What is VDS here?
Minus 0.5.
Minus 0.5.
Minus 0.5 should be less than or equals to. Let us see. It is true or false. VGS is what?
Minus 0.8.
Minus 0.8 minus, what is the V? TP?
Minus 0.4.
Minus 0.4. So it is true or false? True or false?
True.
It is true. So minus 0.5 is less than minus 0.4. So it is true. So it is operating in saturation region. In this way, any kind of numericals you can understand. Normally, this kind of question is asked in the fiscal. Ask this question, and then nowadays it is called NXP. Comparing all this kind of question that we'll ask discuss in future classes in in more detail, but now we'll stop. And by this, what do you understand? That an MOSFET will be on, if its gate voltage is 1 or high, greater than VT. And PP MOSFET will be on if its gate voltage is 0, okay, or its gate voltage is less than its threshold voltage. Okay, that's what we have. Now, small signal modular MOSFET is to be understood. See, one diagram was there earlier, somewhere. No. Yeah, not this one actually. Yeah, this one, but it is already very clumsy. So I'll be using some other place. Okay, this place I'll use. So what happens? Again, let us come back to NMOSFET. So I am drawing a NMOSFET, N plus. Then you have the silicon dioxide, that is insulator. Then you have polysilicon gate material, gate. Drain, this is source. Okay. Now most of the discussion will be with MOSFET, but it is complementary. You have seen the equations also. Everything is reversed. So when you apply a VDS means drain to source voltage. VDS, negative terminal here, positive terminal here. VDS. Okay. If you apply this voltage, if this voltage is larger, what will happen to depletion layer? See, here you have no bias there. Yes, you have grounded it, substrate or p-type body or substrate is connected to the ground or zero potential. Your source is also connected to ground or zero potential. Normally this kind of symbol will not be used. Instead of that, what is used is this way. This indicates a positive term of the battery is connected here, and this indicates that negative terminal of the battery is connected to source. Okay, this potential between drain and source. Now, what will happen to this surrounding of this N plus diffusion? Can you say somebody? I'm surrounding with this. What is that? Is it not a? Remember that this is this body or the substrate. I can denote here also instead of here. I can put here also so that you can understand a bit right. If there is a junction, PN junction, and if you connect, this is P, this is N. Okay, connect a potential or battery like this. What is going to happen in the junction? Tell.
So potential barrier is created.
Potential depletion layer will be formed. First of all, depletion layer will be formed here or not? And a potential
Yes,
barrier will be created, that we have discussed also. So this happens. If you increase if say it is variable and you are increasing the value from 0.5 to say 1 volt, you are increasing. What will happen to the depletion layer? Will it remain the same or reverse bias you are doing?
so it will increase.
It will increase. So that happened here also. Initially, say it was very less, VDS was say very less, 0.3 volt or so. You have increased and given to say 1 volt. What will happen? Its depletion layer around it will be increased. Okay, remember that this is the channel length, original channel length L, but due to depletion layer, due to increase in VDS, drain to source voltage, the depletion layer delta L amount decreases occurring in effective channel length. So effective channel length is nothing but L, let me write in this way, L effective equals to L minus delta L. Are you getting the point? The carrier has to cross this barrier, and so here, entering here, and it is entering into the, coming here and entering into the depression layer, and quickly going to the 10 terminal because there is an electrical field, strong electrical field there, and the drain is, so it is being passed to the drain terminal. Now point is, what will happen to the current if you increase the VDS? We have seen, I think we have discussed also that ID VDS plots, if you draw the plots for a long channel MOSFET, initially it will be linearly increasing when VDS is very less, say 0.3 volt. I am telling as a very small voltage. If it is that, then it is linearly increasing up to this. After that, it is saturating. Condition for saturation region is satisfied. VDS greater than equals to VGS minus VT. This condition is satisfied. For example, in a 1 volt system, say VDS should be greater than equals to VGS equals to say 1 volt minus 0.4 volt is going to 0.6 volt. Possibly when the voltage is going to be 0.6 volt, it will be say 0.2, 0.3, etc. So it is going to be saturated. In case of a MOSFET, before that it is in linear region, current is linearly increasing. After that, current is become flat with the x-axis or parallel with the x-axis. This is the case of a long channel MOSFET, very big, 20,000 nanometer. Earlier it was channel length was L was 20,000 nanometer or 20 micrometer. It was the case earlier, say around 80s. Channel length of MOSFET was 20,000 nanometer or 20 micrometer. Nowadays it is very less than even 20 nanometer. So what is happening is, due to depletion layer, effective channel is getting reduced and current is now increasing with the VDS. This is not a good sign, not desirable. Okay, it is not desirable. So from the equation also, current equation also, we have seen that ID equals to say if I write the saturation region equation, then mu n C ox W by L by 2 into VGS minus VT. This was the equation for saturation region. We see that in the denominator you have the L, and your L is getting reduced. Effective L is getting reduced due to increased VDS, depletion layer widening is taking place. So effective channel is getting reduced. So obviously current is going to increase. So with VDS, as you can see, almost linearly, ID is increasing. Okay, this is the case of short channel MOSFET. Yes, early days also depletion layer was there, but channel length was 20,000 nanometer, whereas your depletion layer will be very, very less. Okay, it's very, very less. Say 1 or 2 nanometer or even 5 nanometer, doesn't matter. 20,000 nanometer versus 5 nanometer is not a big deal. But today, MOSFET channel itself is 20 nanometer or even less, 7 nanometer also. Today, FET are being made with 7 nanometer channel length. So, okay, forget about that. At least you consider 20 nanometer channel length. In that case, if 5 nanometer is the depletion layer width, it is a huge reduction in channel length compared to early days. Do you understand this point? Partly.
Yes.
Yes, sir.
Earlier also depletion layer was there, but channel length was huge. So it was negligible. Its effect was negligible. But now channel length is too less than 20 nanometer. If 5 nanometer depletion layer is occurring, there is a huge difference is occurring in length. So current will be increased. So this effect is called is one of these short channel effect, and it is called channel length modulation effect. Can you remember this? Channel length modulation, CLM. Channel length modulation. Okay. Channel modulation. Due to this channel modulation, if you increase the VDS, current also increases in saturation region. In linear region, it has to increase, but it should not increase in saturation region, but it is happening. Could you understand this thing? Yes or no?
Yes,
Yes,
sir.
sir.
Now coming to the small signal model. Now we have understood something about Mosfet. We have to represent Mosfet in a different way. Model, small signal model. Means, as you can see, that equation of current in a MOSFET is sometimes linear, sometimes some non-linear. It is square law is followed. Okay. So come here, you see that it is squarely dependent with the VGS. It is not linear. So handling this kind of non-linear equation and doing the analysis is troublesome. It is difficult. So what is done is small signal model is made, and signal applied is very small. So excursion in the load line or the movement of some point, operating point is fixed somewhere at the middle of the load line, and it is linearly operated. So for that purpose, what we have to do is, with the understanding that it is a long channel MOSFET, more or less, if it is a long channel MOSFET, we understand that if we increase the VGS, current also increases. Okay, and this property, we can say that it is a voltage controlled current source, because current, I mean, if I say ID, and this is VDS. Okay, for a particular VGS, current will be constant in saturation region. If I consider this, then we can represent this as a current source. What is the current source? Definition of current source? Can anybody say? A current source is what? Ideal current source, for example. Example of a current source, and what is its characteristic? Can anybody say? Yes. Pratham?
So JFET is an example of current source.
Why not a lot of noise in your mic? What is that, Aman? Aman? Aman?
Sir, don't know.
Don't know. Okay. Tell quickly. Madam, I am in the class. After that class. हाँ, थोड़ी देर में हो जाएगा. Huh. So don't know. See, current source is that thing which sources or supplies current constantly, irrespective of the voltage across it. Are you understanding? Current source is that device or apparatus or whatever is that which can supply constant current irrespective of the voltage across it. An ideal current source is nothing but a battery. Okay. Battery voltage little more or less still it will be normally it remains constant at the beginning, but afterwards it because of internal resistance it drops. Still current it supplies constantly till its life is there. So now we see that in case of Mosfet in saturation region it gives constant current. So it is thought of as a voltage controlled current source. Okay, so that is represented by this kind of symbol. As you are saying here, this is a voltage controlled current source. Voltage is your VGS, is the controlling voltage at the gate. To increase the voltage, in the last class we have discussed, increase the voltage, density of carrier in the channel will be increased. If you increase the V1, you have written V1 VGS, then Q increases. If T decreases, C increases, Q increases. If V2 is applied, current flows from the V to A. If V1 increases, current electron density increases, resistance between A and B decreases, current increases. Okay, these things we have discussed, so I hope we should not repeat and say. So MOSFETs can be represented as this thing, voltage control current source. At the gate, with respect to source, you are applying VGS and you will get a constant current which is given by GM VGS, where GM is defined as delta ID divided by delta VGS. ID means IDS, of course. Sometimes I don't write D, and many of the authors are not writing also. Change in drain current for a small change in gate voltage, that is GM. GM is called transconductance. Transconductance of the FET. Okay, that may be FET and FET, JFET, whatever it is. Okay, and controlling voltage is your gate voltage, remember. So it is represented as this. But we have also seen in a short channel MOSFET, current increases with VDS also. That means current is proportional to VDS. So another current source is shown here. Voltage control current source is shown here in this diagram. Second, diagram B. Could you understand? To capture that effect, that is CLM. Understand CLM? What is CLM? Why this is VDS is ID is proportional to VDS? Because of CLM or not? Yes. Aman, are you understanding?
Yes, sir.
Because of channel length modulation, channel length is getting modulated by VDS. Effective channel length is getting reduced. Length is reduced means what? Resistance is reduced. Current is flowing more. You can think of as a simple conductor also. If you reduce the length, your resistance will be reduced, current will flow will be more. Same thing is happening here. So to capture the CLM, we see that current source, another current source is shown here. Voltage control current source, and the controlling voltage here is VDS. It is proportional to that. But we know that a current source whose value linearly depends on the voltage across it is nothing but a linear resistor. So that voltage source, that is which was proportional to VDS, this is removed and put a resistance. Okay. Now we're gradually changing and writing the drawing the small signal model of Mosfet. Right. So this RO is actually capturing the behavior of Mosfet, which is called CLM, channel line modulation effect. This RO, remember that. A small signal resistance, you can say, or it is a resistance due to capture the CLM. Now, normally your body and source of the MOSFET will be tied together, okay, and grounded, okay. But it is not necessary that always it will be. If it is not, then your body terminal means, if I put the diagram in this way, this is the body terminal, okay. If you see the structure, then this is the body. The blue portion is the body, okay. Okay, blue portion is the body. So body is grounded in case of MOSFET, and body for a PMOSFET is connected to VDD. Remember, the highest potential in case of PMOSFET, body is connected to the highest potential, that may be VDD, and in case of MOSFET, body is connected to the lowest potential, that is normally ground in case of digital circuits, but in case of analog circuits, it may be negative supply also. Okay, coming back to our point here. So we see that if body and source are not tied together, it is a separate entity, separate terminal, and body is connected with some different voltage than body voltage, source voltage. Then what will happen? The body itself is going to, body terminal is going to act as a second gate. First gate is this one. Body is going to be acting as second gate. Okay. See, try to understand what we have drawn at the beginning. You said that this is a gate terminal and bottom and that terminal is there. Okay. A negative potential was connected. And in between you have the silicon dioxide. So it's a capacitor. Okay. So it's a capacitor. So if here is connected to that body, and this is the body, say, and this is the source, okay, which is grounded. But here the body and this is gate. The body is not connected, but you have connected another supply here. Suppose here another supply BBS, body to source. Okay, source is grounded, body to source another, and this can be thought of as connected like this. Body is having, so if I can say the top one is the gate and bottom one is the body, why not I can say that body is also another terminal, gate terminal. From the bottom it is acting as a second gate. So body acts as second gate, and its effect is, it also modulates the threshold voltage and the current of the MOSFET. And that's why, see, another voltage control current source is shown, which is denoted as GMB VBS. VBS is the body potential with respect to source. That body potential will be able to modify the ID, okay, current. And GMB is the delta ID by delta BBS. Okay. So this is the complete small signal model of a MOSFET at low frequency. Okay, very low frequency. For analog circuits, this kind of model is good enough to describe or capture the behavior of a MOSFET, but it is not enough for high frequency applications, high frequency amplifier, for example, because at high frequency, capacitance will be playing a lot of role. For example, we have shown earlier also that there will be capacitance between gate and drain, CGD, gate and source, and then you will be having capacitance between drain and body, and another one is body and source. The four pieces of capacitance are shown here. Other capacitances are there. We will be discussing somewhere in the higher semesters. So, but body and source are mostly tied together in case of digital circuits of, especially in case of Mosfets. So, what we can do is it can ignore it. If you ignore it, then CSB is gone because body and source are tied together, and leftover is CGD, one capacitance between gate and drain, CGS another capacitance, gate and source, and CDB is another one. Sometimes it is ignored, CDB, and we can simplify this one, and simplified diagram is shown here. But we will not ignore any of the capacitance, particularly. Yes, we can ignore this one. Sometimes body and source will be tied together, but we'll be keeping these capacitors intact and do the further analysis. Okay, further analysis looks like this. We have already started, but unfortunately I went back to clarify some basics of yours. Okay, so this is the FET based amplifier, CS amplifier, and it's a small signal model is given here. Now you should not surprise what is CGS, what is CGD, get to 10 capacitance, then what is this thing, GM, VGS I was writing here because it was VGS, now it is VI. Okay, what is CDS, drain to source capacitance. RD is capturing what? Tell. Yes, tell what is RD is denoting here. Yes.
Sir, drain to source resistance.
RD is, don't say drain to source resistance. I said what it is capturing, which behavior of the MOSFET is capturing. Yes, kind of resistance only, but tell what is that? Is it not? I said something.
Sir, channel length.
Yes.
Channel length modulation effect. It is CLM. Remember, this term will be coming in future, and you'll be knowing in future if you are taking VLSI subjects, and you'll understand what is that. So it is capturing CLM, or you can say the AC resistance of the MOSFET, built-in resistance. Okay. And other thing is ZL is put here. ZL is put here because once you are going to do the small signal analysis, this will be grounded. So ZL also will come. Yeah, RD or RO. Sometimes it is denoted as RD, or sometimes it is denoted as RO. In the earlier case, we have denoted it with RO, right? It is RO. Sometimes it is written as RD. Remember this thing. Okay, notational difference, nothing else. So this is going to come in parallel. RD or RO is going to be coming in parallel with the ZL because you are going to perform the small signal analysis, right? So in the next class we'll do. What is the time now? Is it over? Oh
Yes, sir.
yes, time is over. So we'll start from here, and we have to go fast. 2-3 lectures I have spoiled to make you understand the basic things of MOSFET. It will come in future also, but I thought unnecessarily you will not understand anything. I should say something. Alright. Okay, then you can leave the class. Leave the class and join other classes.